Okay. So now UTF-32 bit representation. So in Unicode, that is UTF representation, we have three types of representations. One is called UTF-32 representation, 16 representation, and 8 representation. 32 means you will have 32 bits. You will have how many bits? 32 bits, because a decimal number can be represented in 2 bit, 3 bit, 4 bit, 5 bit, 32 bit also, correct? Am I right or wrong? Because if you take 1 as an example, what is the 2 bit representation of 1? No, 2 bit representation. 0, 1, correct? 0, 1. Am I right or wrong? That's the 2 bit representation. If I represent the same thing in 32 bits, you already have 2 bits, correct? You just need to add zeros to the trailing part of that. We have been talking about it, sir. That's called padding. Padding is nothing but you just add zeros. You just add the empty. If you take 32 bits, only you have 2 bits, correct? The rest all will be filled with zeros. In the same way, when you think of 7, what is the 7 in binary? It's 1, 1, 1, correct? If you take 3 bits, 2 to the power of 3 minus 1, 2 into 2 into 2 into 2, it's 8. 8 minus 1 is 7. So, if you fill all the 3 bits to 1, 1, 1, it's going to be 7. If you sum up them, if you sum their equivalent multipliers, it's going to be 7, correct? So, if you want to represent the same thing in 32 bit, you just have to say pad, not add, pad. It's called padding. Padding is nothing but you are basically adding the empty cells, memory cells with zeros, as simple as it is. That means out of 30, only 3 bits are being used. Rest all are been set to zeros, correct? That means 27 bits are being set to zeros. The rest 3 are set to ones. Aren't we wasting memory over here? Are we wasting memory or not? Because to represent 7 in 32 bit, how many bits are you really using? Only 3 bits, correct? Last 3 bits are what you are using. Rest zeros there are no use of them. But still you are giving memory to them. Am I right or wrong? To store 0. Am I right or wrong? So that means the limitation with the 32 bit representation is you will waste lots of memory. Are you guys following what I am saying? So if you represent H for say, see till here all are being padded with 0. How many bits are really being used? 1, 2, 3, 4, 5, 6, 7. So only 7 bits are being used. Rest all are being set to. Aren't we using all this? Aren't we wasting all these memory cells? The same thing with A, correct? How many bits you really require? 7 bits. Rest all are being set to zeros. How many bits you really require to represent space? 6. Rest all are being set to. See, these are all the ones that you are seeing in the red color. They're all waste. You are wasting that. You are wasting that with zeros, correct? You have taken. That means each character that you are trying to represent takes 32 bits. But are we really using them? That's the question, correct? We may use it for the bigger numbers. Imagine you have a big by decimal numbers. That means the symbols with bigger code points. They may need 32 bit. But does this really require 32 bit? Am I right or wrong? Does this require 32 bit? No, correct? Because HA space doesn't really require 32 bit. Am I right or wrong? That means we are wasting lots of memory over here. In this 32 bit representation, wastage of memory is very high. So hardly how many symbols do you use? Let's say Most of the times we use English, correct? English, if you look at all the English characters, they fit in 127 symbols. That's your American standard thing. So rarely we use the symbols that are out of 127. Am I right or wrong? Of course, we use some symbols somewhere in 65,000 range. There are lots of other symbols. We use them. But if you see 95% of the time, you work with this 127 symbols, correct? So that means you are wasting lots of memory. 127 symbols exactly require how many bits? 7 bits, correct? Because I was been telling to you, how many bits 127 symbols require? 7 bits. Of course, you represented in 8 because the lowest granular thing is the byte, correct? Byte is 8 bits. Even though you have 7 bits, you will still pad that with 0. The last bit with 0 all the time, correct? But when you take the poop emoji, that is this is still using lots of other things also, correct? Lots of other digits also. It requires some additional digit when compared to these 3. Because it requires how many? 16. The rest all has been still padded with zeros. That means wastage of memory is very high in this. Am I right or wrong? That means every character that you represent is, every character or every symbol that you try to represent, it will be represented in how many bits? 32 bits. Here in this case, when you say 32, it's 32 bits representation, as simple as it is. Are you following me? In the same way with 16, how many bits we need to represent in 16? 16 bits? Are you sure about it? 16-bit, UTF-16 bit works little differently. We'll talk about it. 32-bit is straightforward, 32 bits. Any number you take, you convert that into binary and pad with zeros. Whatever the values, let's say you take 6, it's going to be 110, correct? You need only 3 bits. Rest all will be padded with zeros, as simple as it is. So that's the reason why this 16-bit representation had come in. That means you are wasting lots of memory cells, correct? That means unnecessarily you are giving memory to it. Am I right or wrong? So that's where the 16-bit had evolved. In 16-bit, how does it work is, it works in 2 slabs. It works in 2 slabs. Okay? So the poop emoji, so if you take 16 bits, you see this, the H representation in 16 bit is this. The A representation in 16 bit is this. The space representation in 16 bit is this. The poop emoji representation in 16 bit, the poop emoji doesn't fit into the 16 bit. You still have one outside. See this? That means you require additional one more cell to store or to convert the poop emoji decimal number into binary. Am I right or wrong? That means you still have one where you don't have space to store, because all your 16 bits are filled, but still you have one which is left over. That means it is not fitting into the 16-bit thing, correct? Am I right or wrong? But still you are still wasting the spaces. Am I right or wrong? Are you still wasting the spaces? You're still wasting the spaces, because you could see these are all been represented in red color. That means you're still wasting the spaces. Okay? So, but you see this, but this is as compared to 32 bit, it's still fine, correct? Because the number of bits got reduced from 32 to 16. The wastage got little, still fine. Am I right or wrong? But when you want to represent a poop emoji, is it fitting into this? It's not fitting, correct? Because it requires, to represent a poop emoji decimal number, it requires 17 bits. But you have how many bits? So, 1 is outside of this. So, what is the solution for this? So, that's where, so poop emoji doesn't fit in the range of 65,000. That means the maximum number that you can represent with 16 bit is 65,576 or something like that. Correct? So, but the number the poop emoji has is 1,28,000. That is greater than 65,000. So, you cannot fit that in to 16 bit. Now, what is the solution for it? So, that's the reason why we have something called surrogate pairs. Okay? Surrogate pairs is very simple. Try to understand it. It's very simple. It's a beautiful concept. It's a beautiful concept. Trust me, guys. Such a beautiful concept it is. So, let's understand surrogate pairs with an example. Right? So, now the step one to basically to derive the surrogate pairs is like this. So, you need to subtract. So, your code point, the code point for poop emoji is in decimal it is 128169, or in hexadecimal it is U plus 1F349. That means when you convert decimal into hexadecimal, you will get 1F349. U plus means Unicode, as simple as it is. So now you are taking a Unicode, you have to convert this into binary. We looked at it, correct? In our previous step, I had shown you the hexadecimal number to a binary mapping. So you just need to take one is 0001. F is 4 ones, correct? Go back to the sheet, you will understand. F is what? 4 ones. 0 is 000. 1 is 0001. Then what we have? Then you have 349, correct? 3 is what? 011, 0000011, and 49, correct? 4 is 0100, 9 is 10001. So you just need to represent that in binary, as simple as it is. Now you need to do minus of 10000000. That means you need to take this number and you just need to minus of 10000000. So you just need to do 00001, 0000, 0000, So this will come as it is, this will come as it is, this will come as it is, this will come as it is. So 1 minus 1 is 0. 0 minus 0 is 0, 0 minus 0 is 0, 0 minus 0 is 0. Okay? So when you convert back, does this have any value? 0, 0, 0 doesn't have any value, correct? This is just a 0. So now when you get a trailing 0, you can ignore it. There is no value to it. So when you convert this back again into hexadecimal, it will be F349. So 1 got removed, correct? See this? There's 1 F349. 1 got removed from this. You have F349. Okay? Now convert the resulting value to binary. This is how it looks like. Okay? Now split the 20 bits into 10 bits proportion. That means you have how many bits over here? 1, 2, 3, 4, 20 bits, correct? Because you have 5 numbers. 5 into 4 is 20. Take first 10 bits. You half them off. You just need to half it. That means split the 20 bits into 2 10 bits proportions. That means take first 10 bits and you call that as leading surrogate. And you take next 10 bits, you call that as trailing surrogate. That means your number that you are trying to, your poop emoji that you are trying to convert into a decimal, it's not fitting into 16 bits. Now what we did, we had applied this formula and we had derived the surrogates, respective surrogates. So what is the surrogates we got? Leading surrogate and trailing surrogate. That means the same image is now been represented in 2 surrogates, as simple as it is. So now The step 4 is add 0xD800 to the high surrogate. That means you need to take first 10 bits from our previous step and you just need to add this. So this will become, so you just need to add it, correct? So it will be DX83C. It's called, the result that you get from it is DX83C. Now you need to take the low surrogate and you need to add 0xDC00. So you will get a number like this. Now this is called as first surrogate, this is called as a second surrogate, as simple as it is. That means if you wanted to represent poop emoji which doesn't fit into the 16 bits, now you splitted that into two surrogates and you will represent them in two 16-bit representations, as simple as it is. Exactly, this is how you need to do. You just need to take this and plus with the first 10 digits, and then you need to take this and do an addition with the next 10 bits. Anything, any sort of a conversion you do with the 16-bit which is greater than 65,000, you need to do this. Anything that falls under 65,000 can be represented easily in 16-bit. Am I right or wrong? It can be easily represented in 16 bits. Correct? Because you take a max value of 16-bit, it is 2 to the power of 16 minus 1. It would be somewhere around 65,576 or something like that. So anything less than that can be easily represented in 16-bit. But anything beyond it has to follow this procedure. Because you cannot represent that in 16-bit. Am I right or wrong? Because you don't have enough bits to represent that. Correct? That's the reason why you are basically splitting into surrogates. So you got how many 16 bits over here? Two 16-bit representations, correct? So this is one 16-bit thing and this is another 16-bit thing. Are you guys following? So anything that doesn't fit into 16-bit has to go for the surrogate approach. That means computer will calculate the surrogate pair and it will basically get the low surrogate and high surrogate. Are you guys following me? Are you guys following what I am saying? So the high surrogate needs 16 bits and low surrogate need 16 bit. 16 bits, correct? This is 16 bit and this is also 16 bit. That means poop emoji requires how many bits? 16 plus 16, 32. That means how many bytes? 32 divided by 4. Sorry, 32 divided by 8. 4 bytes. That means poop emoji require how many bytes to represent in 16 bits? 4 bytes, as simple as it is. But what about A? What about H? How many bytes it requires? 2 bytes. Because in 16-bit, 16 divided by 8, 2. And what about space? 2. And what about this? A character? 2 bytes. That means in 16-bit UTF-16, each character or each symbol require 2 bytes. 2 bytes is more, correct? For 127 symbols, you are giving additional byte that can be represented in 1 byte. Am I right or wrong? Can we represent 127 in 1 byte? Sorry, 127 symbols. First 127 symbols in 1 byte, 8 bits. If you take first 127 characters, which are our ASCII characters, how many bits they require? 7 bits, correct? But still you give 1 bit because you can represent anything that you can represent in a computer as a byte, and byte is 8 bits. So that means first 127 characters doesn't require 2 bytes. It requires exactly 1 byte. Am I right or wrong? So, but still you are giving how many bytes over here? 16 divided by 8, 2 bytes. So how to avoid this? How can we still reduce our memory? That's a question, correct? See, we are talking about the space consumption over here. How to optimize it? That's what we are talking about. Because we have been keep telling from the very beginning session. What are the 2 important components of your computer? memory and CPU. You have to use them efficiently. Am I right or wrong? So we are talking about the memory first and how to optimize it. So with 16-bit when compared to 32-bit, this is still okay. Am I right or wrong? But can we further optimize it? Is the question. We can do it. That's where UTF-8 came in. Is this clear to everyone, by the way? The high surrogate and low surrogate thing. Is it clear to everyone? So, the bad thing, we are still wasting the spaces for zeros for these three. The good thing is poop emoji efficiently utilized the memory, but still wasting the spaces for this with zeros. Am I right or wrong? Because you see here you have lots of red color things as the zeros over here. Now, as a core point less than or equal to 65,000 requires 16 bit, more than that requires requires two 16 bits, which are the surrogate pairs. Did you guys understood the calculation of surrogate pairs? You have to practice it, then only you will understand it. Are you guys following?